Ladies and gents, hello, Mr. Lesham is here, and we are back in differentiation. We had a little bit of a break with inverse function, but we're back in differentiation. Now, the last couple of lessons we worked very hard on calculating the derivative, okay, using first principle. And I'm not going to go through that, but I just want to show you. Okay, we've done stuff like that. Given a function f of x equals 3x squared, we're using first principle with that h, which is very close to 0, but not really 0. And it took us probably half a page to find out the derivative. Okay, f prime means the derivative, which is the gradient. Okay, the steepness of the slope, and that comes to 6x. Do you remember doing stuff like that? Yeah.
Yes, sir.
I'm going to show you now a way of doing it in less than a minute, which is very, very easy. So I'm going to write in red. So let's say f of x, we'll use the same number, 3x squared. Okay? All you got to do, if you want to know the derivative, okay? First of all, you write the x, and the power, you take it minus 1. So 2 minus 1 is 1. So x to the power of 1, we don't need to write it, it's x. Now we take the 2, and you smash it with a number here. So 2 times 3 is? Look at that.
What? Is that the answer?
That's the answer.
So I've been doing that method the whole time.
But you should have. Because guys, this method is called first principle. And you need, I'll answer all the questions, guys. Let me just clarify. You need to be able to use first principle. And you will, in fact, have one question in the test where you'll have to do first principle. If I ask you to calculate the derivative or the gradient using first principle, you have to do that. But if you are not asked to use first principle, so look carefully, if you're not asked to use first principle, and you'll have at least 4 places where I'm going to ask you to calculate gradient and not using first principle. I'm not going to tell you don't use first principles, I'm just going to say nothing. So if you're not asked to use first principle, you are going to be mad if you're going to use this method. All you got to do is just do the method that I've showed you here, and I still need to expand on it. We're not finished with that yet, okay? I still need to clarify. I'm sure it's not 100% clear for you. But before that, any questions? Yes. Give me another function. Different one, not with square, something else. F of, or g of x. Give me something. Come on.
Can I give you like
any number, power, any number, yeah.
20
to
the power 4.
20x to the power of 4. Okay. Alright. I want to find out the derivative of x. So, we start with the x. What will be the power of x now? 3. It always goes down 1.
6.
So if it was 2, it went to 1, the 4 becomes 3. Okay? And now we take the 4 and you times it by the 20 and you're right, you get 18. That's it. Now if you tried, if I was extremely mean and asked you to calculate that using first principle, it will take you 2 pages.
Oh my word.
And you probably would have made a mistake. But I wouldn't do that, that's too mean. So you can see how the power of these differentiation rules are so helpful. Okay? Let me pause, clear out, and we'll do a bunch of examples. More examples, guys, more examples. Okay? I've got a function, f of x equal x to the power of 4. What is the derivative? We'll start again. What is the power of x? 3. And then what I have in front? 4. As easy as that. Okay? Now, okay, because it's so easy, I'm going to just add one little thing. And it's just what we call notation. Okay? So it's not anything different, it's just notation. Sometimes, instead of f of x, we say y equal x to the power of 4, right? Now, if I want to write the derivative of y, okay, I don't have, here I have that prime, but here I can't have because there's no x. So what I do is I write dy to dx.
There are a lot of ways in the
dy to dx. You've seen that in the calculator, isn't it?
More than
Okay?
one.
Right? And it's the same thing. The derivative of y is it's going to be simply 4x power 3. Now, I want to just give you an idea where that dy to dx is. Okay? What is delta y over delta x? Remember that one?
Gradient.
It's the gradient. But that will be your average gradient.
No,
So what we're doing is in the limit where h approaches 0 and our difference between the point is so small, what we call it, we write dy to dx. Okay? So that's it. But you don't really need to know. You just need to know that's just another way of writing the derivative. Okay? There is two more ways I'm going to do it. Okay? One, let's say I have 3x to the power 5 over 5. Okay? Now instead of writing f of x equal to that, what I'm going to do, I'm going to write this whole thing and I want to do the derivative of this. Okay? So I'm going to do d of this to dx. That basically means that I want to do the derivative of this. Okay? It's the same as if I wrote f of x equals 3x to the power 5 divided by 5, and then I do the derivative. Okay, maybe I should start with that. If I have 3x to the power 5 divided by 5, what's the derivative of f?
15.
Let's start with the x. Always start with x. What will be the power of x? 4. Okay, and then I've got the 3 over 5, and I need to time it by 5, right? And then what can I do? This is not 35, this is 3 times 5. What do I do now?
Oh my word. You cancel the living hell out of it.
Cancel the living hell of it. Okay? So what do we have? 3x to the power 4. Okay? So the 5 jumps out, get ambushed. You like that? There's a little ambush. That 5 is lying down there. Annihilates it, and we end up with a 3. Are we happy with that? Okay. Now, what does this mean? This means basically, look, I've got a function here. I want you to do the derivative with respect to x. It's just a notation. Don't get scared by it. It's the same thing. It's going to be 3x to the power 4. So either I say, right, this is the function, this is the derivative, or just, what is the derivative of this? It's the same thing. Are we happy with that? Okay, let's do one more. Let's do. It always works. It always works. This will always work.
That x to the power of 4. The derivative is only 4x to the power of 3.
Yes. So the 4 jumps up.
Use 2 there, so 2 to the power of 4 is 16. 4 times 2 to the power of 3.
I mean, I just pause here. Sorry. So I had one more function that I was going for. 5x. Okay. What will be the derivative of 5x? Well, let's use another notation. Let's use it like this. Y equals 5x. What will be dy to dx? I just want to get you used to this. What is it?
1.
X.
5.
Okay. So x, what you wanted to say, Mark, is x to the power of 0, which is 1, right? But you still have that 5. Don't forget that 5. So the answer is 5. Okay? We happy with that? Don't forget the coefficient. But now I want to show you another annoying notation. Okay? So we can write it like this. Instead of doing that, I can say with a capital D. And normally we use squared brackets. So this thing tells me, look, this is your function 5x. I want you please. Square bracket is the please. No, I'm just joking. The capital letters. Okay? It tells me do the derivative of this with respect to x. That's another in words. And guys, I'm going to use all these notation in the test. I'm going to write that and ask you to calculate that. I'm going to write that and ask you to calculate that. I'm going to write that. Just write straight away to calculate that. Okay? That's still fine. And sometimes I can say in words. Okay? What is or differentiate the function f of x equals 5x with respect to x. With respect means do the derivative with respect to x. Are we happy with that? Okay, let me see if we need to do any more examples. Okay, sorry. So our last example before you work a bit is to find the derivative of this function. Now I know JD will be able to tell me straight away what's the derivative of that because he told me that last time. Okay? We actually spoke about that. Okay? The derivative of the function f of x equal 2, it's a horizontal function. The gradient is 0, so obviously that should be 0. But let's see if we can use these rules. Okay? What are the rules? Okay, well, instead of 2, I can write, where's my x? So x to the power of, well, actually, this is not going to work. Sorry. So let me just pause for a second. So that is a little bit of an exception here because I don't have an x. But we remember JD remind us that this is actually 0. Okay? Now, okay, one more thing I like. One more thing before I get you to actually do some work on your own. I want to write down a rule here. If I've got f of x equal a times x to the power of n, and n, this is my, what you call it, this is my exception, n is not equal to 0. In other words, I must have an x there. The derivative, maybe somebody can figure out, what will be the derivative? A and n are just numbers. It will be a n, you're right, you smashed a on the n, times x to the power of what? N minus 1, well then come. Okay? So that's the rule that you need to remember. Are we happy?
Yes, sir.
Let's work. Simon, tell me how on so there's a couple more rules. Well, the one rule, they call them special cases, actually comes from that. What does that mean? If n is equal to 1. In other words, in this case, I'll call it g of x is going to be ax, because n is equal to 1. What will be the derivative? Okay? It's just going to be a. Okay? But I could use that here. I could use that there because we had one like this. Okay? The 1 became 1 minus 1 became 0. Ax to the power of 0 is a. That's fine. There is one special case. Okay? So this is really, we don't need to write that. That's inside here. But there was one case where it is a problem, and we had to write another special case when n is equal to 0. Okay? When n is equal to 0, if f of x equal to a, then the derivative, what is the derivative? A can be any number, but there's no x there. Then the derivative will be 0. So that is a special case that we need to add. I will put a square around it. This is actually inside here. This is not a problem. But this is a special case. We can't use that.
That's cool.
Okay, guys, I'm going to write down, well, not for you in the camera. I'm going to see you in a bit. These things, okay, I forgot to record it. If you've got a function or polynomial where the power of x or x is at the bottom, okay, first of all, before we calculate the derivative, we're going to rewrite it as a negative exponent. Right, as x to the power of minus 4. Now we use the same rules, okay, to calculate the derivative. The minus 4 jumps up, minus 4 times 3 is minus 12, x to the power minus 5. But we've learned that we got a good practice is not to write negative exponent, even though mathematically there's nothing wrong with that. It's better if you write minus 12 or the x to the power 5. Okay? Now, if you've got this case, okay, we've got square root of x, okay? Again, to be able to use the same rules, we're going to have to write it as a rational exponent. Square root of x is x to the power of half. And then we use the same rules. The half jumps out, we get half minus 1 minus half. And then we push it down to the bottom to become positive half. And then what is x to the power of half? It's the square root of x. So that's a nice, polite way to write. We have a lesson tomorrow, eh?
Yeah. Every day.
Every day? Every day I see you, actually.
Every day, bro.
Every day I see you. Okay. So.
That also necessary because that is a positive exponent.
It's a positive exponent. Yeah, but it's not. We don't want fraction exponents, so we always turn it into a suit. Okay. Right.
Yes, sir.
Bye bye. Let's practice this then. Serio.